So today we shall discuss about principal stresses. The concept has already been introduced to you in the subject of mechanics of solids. So again, this will be used in the design of machine elements. What are these principal stresses? Why these are important in design? See, in the earlier classes, you would have handled problems involving simple loading situations where you have only one type of loading, like tensile loading or compressive loading. This is uniaxial. The other case of loading is bending, or only twisting, torsion loading. So it was easier for us to uh, analyze the stress if and ensure that the stresses induced in the component does not exceed the limiting values, be it yield strength or ultimate tensile strength. There are situations in reality where several types of loads act simultaneously, that is combinations of axial load, bending load, and twisting load. How to handle this kind of a situation? For example, shaft carrying gear will be subjected to bending as well as torsional moment, right? So in that case, what will be the maximum value of the stress induced in the component? Now that we have a combination of stresses, how to find the net effect of that combination, right? So we will start with simple loading situations like biaxial loading and find the net effect of that, right? And then employ that in design. So that is why it is necessary to determine the state of stress. When we say state of stress in the element of a component, we mean that we have to specify the all types of stresses acting on the element, magnitudes of all types of stresses. What are those types of stresses? We shall see. So here we have a simple plate subjected to two-dimensional stresses, right? Let us understand this notation in the next slide. We have normal stress, we have shear stress. So we basically classify the stresses into two groups, normal stress and then shear stress. So we know normal stress acts perpendicular to the area under consideration, while shear stresses act parallel to the area. So coming to the notations, please look at the figure. Sigma is reserved for normal stress and tau is reserved for representing shear stress. When we write sigma suffix x, it means that the normal stress is acting along the x direction. Similarly, sigma y, normal stress along the y direction. Then what is this tau yx and tau xy? See, in this, the first suffix, let us take, well, before that, the sign convention for tensile stress is positive and compressive stress is negative. This is known to us. Yes, let us come to the shear stress, tau xy. What is this x? The first suffix indicates the plane normal to x-axis. Y indicates the direction along which the shear is acting. You can see this in the figure, tau xy, it is acting in the upward direction in a plane normal to x, right? And likewise, tau yx, plane normal to y direction and acting along x direction, shear stress. Okay, so this is the notation we use to specify the stresses. Now let us take a simple case of this element and examine the stresses on different planes oriented at an angle theta. So let us take this an element acting in an oblique plane, a plane inclined at theta with respect to x-axis, horizontal line. Okay, so we have two components, normal stress and as well as shear stress, right? So now you consider the equilibrium and then we can do it, but you have already done it in mechanics of solids, how to get this equation. Okay, so let us not do it again. So we will get this expression for normal stress sigma and shear stress tau. What are we interested? We are interested in finding the net effect, maximum value of the stress, normal stress and shear stress. Okay. Next, what we do is we differentiate the normal stress equation and set the result equal to 0. So you will land with this equation. tan of 2 times theta is equal to 2 times tau xy divided by sigma x minus sigma y. This will give actually two values of 2 theta, right? That is two planes on which you have maximum value of the normal stress, and on other plane you will have minimum value of the normal stress. And this maximum value and minimum value, we call it as we denote it as sigma 1 and then sigma 2. You substitute this in the previous equation, right? You will get sigma 1 and then sigma 2 expression. Sigma 1 will give plus and sigma 2 will be minus. And these sigma 1 and sigma 2 are called principal stresses, because when you write d sigma by d theta, it means only normal stress. The stresses are not varying with respect to theta. Okay, so these are stresses which are on which shear stresses are zero, right? Principal stresses, and the plane on which they act are principal planes. Next, we have to find the maximum value of the shear stress. You take the shear stress equation, differentiate with respect to theta, equate it to zero, you will get maximum value of the shear stress. We call this as principal shear stress. We can use this analytical method or you can also apply graphical method to determine the stresses on inclined planes. For 2D, we mostly use Mohr circle diagram, right? So where we graphically represent the stresses. So how to construct this? See, we construct this Mohr circle diagram in the design of machine element. So please go through this concept. This is very, very important. Please don't underestimate the importance of this Mohr circle in the design. So this is the Mohr circle you would have drawn in the mechanics of solids. Let us relook into it again, how to construct also. So first you will be given with a state of stress acting on an element. When we say state of stress, it means we are giving the magnitudes of different components of stresses acting on the element. Sigma x, sigma y, right? We don't give sigma 1 and sigma 2. And shear stress. What you do is you plot them. So Mohr circle is basically constructed on two axes. Horizontal axis, that is abscissa, is reserved for the normal stress, and ordinate is reserved for shear stress. Okay, tensile stress is positive and shear stress is negative. What about the sign convention for shear stress? See, if the pair of shear stress rotate the element in the clockwise direction, it is positive. Otherwise, it is negative. So please remember, clockwise rotation is positive and anti-clockwise rotation is negative. Now let us see how to construct here. So we have sigma, see now that we have sigma x value, sigma y value. So you plot it. So sigma x equal to OA, right? Origin is O. Point, mark this OA, and similarly sigma y OC, right? On the same axis, normal stress axis. Okay, and then you will, if you are given with shear stress, what you do is you you can draw it. Usually tau xy is equal to tau yx for the equilibrium of the element. Okay, if only tau xy is given, you can assume tau xy equal to tau yx from equilibrium considerations. You draw a vertical line whose height is equal to tau yx. Then similarly, from point A, draw a vertical line downward equal to tau xy. Join point B and D. So this line BD will intersect the x-axis, that is on sigma axis. Let us use the word sigma axis at point E, which is the center of the Mohr circle, whose radius is ED. Now with E as center and ED as radius, you draw a circle. So the circumference of the circle will intersect the sigma axis at 2 points, F and G. So OF will give us the sigma 1, that is principal maximum value of the principal stress, and OG will give us the minimum value of the principal stress. So from sigma x, sigma y and tau xy, we can find sigma 1 and sigma 2. The other way around is also possible. If you are given with principal stress, you can find the state of stress on the element. Reverse work. So here point F indicates theta equal to 0 and point G indicates theta equal to 180 degree, and normally we move the plane in the counterclockwise direction. We will see how to find the stresses on. So let us take an example. In this case, the state of stress on the element is given sigma x, sigma y. We need to determine the stresses acting on the element inclined at an angle of 30 degree. So how to do that? We don't have the value of shear stress. Okay. So as usual, let us mark sigma x, sigma y. Take the average of that, locate the center by 2, right? We will get the center, and that is 55 MPa. Okay, so you locate the center. So now we have to draw the circle through points A and B with center at C and radius R. How do you estimate radius R? We have the equation. Okay, shear stress here it is not given, so you can take it as 0. Fine. So from this you evaluate the radius 35 MPa analytically, since we don't know shear stress, right? So now you draw the circle, more circle. So now let us evaluate the stresses at an angle of 30 degree. So as I mentioned, so point A is actually theta equal to 0 plane, that represents theta equal to 0 plane, horizontal plane. We have to identify a plane at 30 degree. So here actually it is 2 theta, right? So 30 means 60 degree. By 60 degree we have to mark a line passing through the center, point D. This is theta equal to 30 degree. The coordinates of D are actually the state of stress acting on the plane and on the element inclined at 30 degree, right? So what is this x coordinate? X coordinate is simply OC, that is sigma average, plus R cos 30, right? So it is 72.5. What about the ordinate? That is the shear stress value. It is simply R sine 60, but we are using negative sign because we are rotating the plane. That is, the shear is in the counterclockwise direction, so it is negative sign. So minus 30.3 MPa. Similarly, you can find on a plane represented by point D prime, which is not asked in the problem, right, at 120 degree, the same fashion, but you will have a positive stress. Okay, sigma x value is slightly, sigma normal stress value is slightly different. Okay, so we have actually found out the stresses inclined on a plane at 30 degree, right? So these are the normal and stresses, 72.5 MPa and 37.5 MPa, and shear is 30.3 MPa. Note that sigma x plus sigma y is a constant, right? What do you mean by that? What is your interpretation on that? So you please tell me during the live class. Okay. So these are the references I've used. Thank you.